Now we look at some more game algorithms. Now, why do we play a game? Why game? Answer: to win. So, can I ask the question, how win? So, you win if you are better than opponent, or if your opponent is worse than you. This is your standard. This is your opponent's standard. You become better than your opponent. Or let's say this is your standard. You make your opponent worse than you. You winning is a function of you winning in a little series of games. Right? Let's say you want to win in Coco. You're sitting down with your team. Right? There are 3 players running. Now, to win this game, you need to first win among these 3 people. To win among these 3 people, you first need to target one guy, second guy, third guy. Then they will go out. Then the next 3 will come in. So can I say this is a mini game? You need to win this mini game to go to the next mini game to win the entire game, right? So like this, you need to face 3 into 3 people. Yes or no? Great. And also your game is a function of your opponent, bro. What do you mean by function, bro? It's maths. Function means it depends. Your game depends on your opponent's game, right? Your opponent does something really nice, you will have to think a lot. Yes or no? Your return of investment, your ROI, is a summation from time t to time is equal to when the game ends, right? It starts from zero till the end, and the return of investment is how good you are versus time. So your level of expertise kind of increases like somehow. This thing is called a learning curve. Great. So humans have a lot of tactics in playing stuff, right? When humans play, you need to analyze, you need to strategize, and you need to have tactics. After all this, you need to move your coin or your piece or your game player, right? So kind of tell me like this. There are a lot of chess playing AIs, Deep Blue, right? Deep Blue was just one CPU like that, one big CPU, which they had trained with a lot of models loaded into it, and they made it play chess with Gary Kasparov. I think a lot of people. So it kind of bets everyone at chess. So Deep Blue is officially the grandmaster of chess. How does it do that? Great question. How does it do that? So let's say this is the starting of your chessboard. Okay. Let's just assume your chessboard right now consists of only 16 squares. You have king, queen, bishop. When will your board be like this? Only when your time is equal to 0. Because at some point you will move something or opponent will move something. So now at time t, you have options. Okay, technically you don't have options here. Okay, we'll make options. We'll make way for options. Great. King, queen, bishop, bishop. Pawn, 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 pawn. Now you have an option. Move this or you move this or you move this or you move this. So can I say at t is equal to 0, you have 4 options to do. Now, if your condition is like this, you can move like that. So let's say if you moved p here and your opponent has an option. So he will move this here because he gets to cut your coin, right? It's a conditional based thing. So this is one level. Same thing, you go another level deep. This is 2 levels. So the more you look ahead, so if you say, okay, I have equal chances of winning here. I have 0.5, 0.3, 2 chances of winning here. So if you know 2 steps, can I say you will never take this step knowing that it will lead to a 0.3, and you will definitely take this step? Yes or no? So you basically look ahead and evaluate. So you keep looking ahead and you keep looking ahead. How much can you look ahead? See, to put things into perspective, one human cell has 3 into 10 to the power 9 molecules, right? Like H2O, H2SO4, etc. A lot of molecules. One molecule is approximately 5 atoms on average. See, H2SO4 has 4 plus 1 plus 2, 7. H2O has 3. So on an average, can I say 5? Human body has approximately 5 trillion cells. What is trillion? So can I say per human 5 into 10 to the power 12? Every cell contains 3 into 10 to the power 9, and everything contains 5 molecules. So this many number of atoms. How many billion people are there in the world? 8 billion, right? 12 billion. I think it crossed something. Great. So 8 into 10 to the power 9 into, I want to model humans for 365 days in a year, 24 hours in a day, 60 minutes in an hour, 60 seconds in a minute, and that was for only 1 second, right? Into every nanosecond, into this entire atoms. Now, just think how big that is. 10 to the power 9, 9. There is another 9. There is another 9. Like this itself is a lot. 29, 30, almost approximately 50. 10 to the power 50 combination, something like that. There was a guy called Claude E. Shannon, right? You have some time, then take a look at this guy. It's pretty legendary too. He said at any point in time in chess, 10 to the power 120 static values must be calculated. If you want to model the earth for a few nanoseconds, in nanosecond precision, you want to model it for a year, you need that many Wherever. Great. You need these many atoms, right? So basically it's impossible. So we cannot model chess. We must use sub-optimal algorithms. Can't always choose the best. So our goal is to look as far and as deep as we can. So we are going to use an algorithm, right? So this is called MinMax algorithm. Tomorrow, what if they give you a graph like this? And they say, if you do this, you will get to 8. Now, MinMax. How to do MinMax? Number one, you will always have a graph like this. You will always have a graph with all the bottom values filled. Now, what do? You'll see, you want to win. Don't you want to win? So this is always maximizing. You want to maximize, meaning you want the best option. Now, min-max algorithm is called min-max for a reason. If one layer wants to maximize, your other layer will minimize. Dot in a different color. So you alternate with maximize and minimize. Right. So can I say this is maximize, this is minimize, this is maximize. So we call it max layer and min layer. Simple. What do? Max. Oh, okay, this doesn't matter. Great. So you need to find the minimum now. So can I say, okay, which is the minimum in this 2 and 7? Who will come and sit here? 2 will come and sit here because 2 is minimum. Now among 1 and 8, who will come here? 1 will come here because 1 is minimum. Okay. Now maximizing will look at, who is bigger? Is max. 2 is max. So we'll take max and put 2 here. Done. So your ideal path, which has been selected by the machine, will go something like this. Start from 2, go here and reach 2. Right. Tomorrow if they ask in the exam, draw this and draw the direction of it. Right. How do you know the direction? It's literally the same node. You just follow it. Great. Now B is called branching factor. Here B is equal to 2. It has 2 branches every time. 2 branches every time. And depth is equal to 2. No, depth is equal to 3 because this is level 1, level 2, level 3. So number of nodes in this kind of perfect tree would be B power D. So it will be 2 power 3. So it will be 8. Oh no, your depth will be 0, 1, 2. So your depth is basically 2. So your number of nodes is equal to B power D. That is equal to 2 power 2. That is equal to 4. Bro, there are 7 nodes. No, you need to look at only these nodes. Okay. So this is your min-max DAC. This is also called an adversarial algorithm. Why is it called an adversarial algorithm? Who is an adversary? An adversary is called an enemy, right? And we do it in the bottom-up approach. Now, why is chess? Tomorrow, if they ask you, why can't we calculate for chess? Why chess is equal to hard? Number one, full-fledged algorithm is equal to not possible, since combination is equal to infinitely many. Number two, full-fledged algorithm is not possible. What do you mean by a full-fledged algorithm? You can't develop the perfect algorithm. Now, if-else algorithm, it requires 10 to the power 120 combinations. Therefore, not possible. Third, one look ahead. This is too little, right? We can't just look at one. So what do? We use a min-max. You will maximize and your opponent will minimize your chances of winning. He won't minimize his own, so keep that in mind. Great. We look at something a little more complex. Great. Tomorrow, if they give you an algorithm like this or a graph like this, right? We'll write down the numbers 4, 8, 9, 3, 2, minus 2, 9, minus 1. Number one thing, what do? We first write layers. U is equal to maximize. Who's playing the game? Who's the boss? You're the boss. So you need to first put your foot down and say, okay, I will maximize. Then my opponent will minimize. Then I will again maximize. So you are a max layer, then there is a min layer, then there is a max layer. So there is a max layer at the bottom. 4 and 8, 8, 9 and 3, 9, 2 and minus 2, 2, 9 and minus 1. Minimum of this. 2 is the minimum of this. 8 and 9, 8 is the minimum of this. Max is 8. So now tell me the path. 8 goes here, 8 goes here, 8 goes here. So this is the path that it will follow. Right. So the more deeper you go, the more probability that your min-max will work better. So can I say that your total minimum, your total minimum is minus 2, total maximum is 9, your branching factor is 2, your depth 0, 1, 2, 3 is equal to 3, your nodes is equal to B power D, that is equal to 2 power 3, that is equal to 8. You'll do this, they give you any size, you'll do it. Great. Now, how do you do this intelligently? So check this sum. Yep.
What makes the difference between min-max and adversarial?
Min-max is an adversarial algorithm. It's called an adversarial algorithm because it has an adversary. All right. So min-max is same. 2, 7. How do we do it normally? You will maximize, opponent will minimize. So you first write this is a minimum layer, this is a maximum layer. So minimum layer will have 1 here, this will have 2 here, then this will have 2 here. So this is the path. No, I don't want to do. You want to make it simpler. What do? You say, okay, I will first look at 2. Now, this is my minimizing layer. Where is my blue? This is my minimizing layer. This is my maximizing layer. If I have anything that is lesser than or equal to 2, I will take it. But we don't know anything else. No, so we'll say, okay, what's this? It's 7. Or 7 is bigger. So, okay, I'll take 2 itself. So now this node has been set to 2. Now, this 2 will be pushed up. So now look, you have a 2 here. Let's say some number x comes. Now tell me, if your x, your maximum will be 2, you want something that is greater or equal to 2. Yes or no? So you want something that's more than 2 here. If your x is more than 2, it will become 2, right? Now, can I say that I want something greater than, now once this whole thing is complete, push to the next layer. Understood? Great. Now I look at 1. My min layer will say if I get something lesser than or equal to 1, I'll give it to you. But max layer is saying if I want something greater than or equal to 2. So you tell me something. Does it matter if there is minus 100 here or if there is 1000 here? No. Why? If there is minus 100 here, this will give minus 100. But minus 100 is less than 2. So this will take this path anyways. If it gets 1000, it is anyway going to select 1 from minimum. And this 1 will go, can't go here because 2 will be taken. So whatever the value here, we don't care. So we are ignoring. So you see, out of 4, we only looked at 3 nodes. Yes or no? Yep. So great. That's it. Let's try another sum. Okay. Okay. Now you should know which layer is yours. Max, min, max. Okay. You always play to maximize. Your opponent plays to minimize your chances. You always play to maximize. Great. Now let's look at one by one from the left. 4. There is a max layer. If there is anything greater than or equal to 4, I'll take it. Now there's an 8. Wow. Okay, so this is an 8. This is done. I'm pushing it to my next layer. So now it's a min layer. Anything less than or equal to 8, I will take it happily. Now we look at 9. Okay. Now max layer is saying I will take anything greater than or equal to 9. That's only going to be my value. Something greater than 9. So if you draw a graph here, your max layer is saying something greater than 9. This is your 9. It has something greater than 9. Your min layer is saying I want something lesser than 8. Your min layer is saying I want something lesser than 8. So you see this difference here, it's not even overlapping. That is when you say, I will skip this value. Whatever you give me, this is going to go with 8 from this side. So we skip this and we confirm 8 here and we push it to the next level. So max is going to say, I'm going to take anything that's greater than or equal to 8. Right? Okay. Now we'll look at 2. Now now you can't directly go from here to here to here. We can't look 3 levels. So let's look only at this triangle. Look at 2. Max layer will take something greater than or equal to 2. How do we know what it takes? We have not even, now you can't push a value before you complete the triangle. Yes or no? Okay. So we'll first complete this triangle. We'll check minus 2. Okay. So the value is 2. So we set it to 2 here, right? Here the value is 8. Now this 2 will be pushed up. It wants something lesser than or equal to 2. Yes or no? But max layer wants something greater than or equal to 8. So if you look at it, this wants something greater than or equal to 8. Your min layer will give something that's lesser than or equal to 2. You see this clear difference in boundary? So it will say, I don't care what's here. And your value will be set as 8. So your optimum path is this. Bro, is this different from min-max? Will it give me the same answer as min-max? Absolutely same answer. Wasn't this the answer in our last 2 cases? See, this also went to 8. Right. So this is called alpha beta pruning. Why is it called alpha beta pruning? Because there are some alpha prime, beta prime values which you don't need to know. Honestly, this is everything you need to know, right? So tomorrow if they give you a sum, you'll know what to do. Take a look at one more small example. Okay, do it. The table works like this. So you first have a step number, then you have the static value, then you have your layer A, layer B, layer. Okay, now you name your nodes. Okay, let's name our nodes. Let's give it name. Where is yellow? So can I just name them A, B, C, D, E, F, G, anything you want. So now we're going to write the names of our nodes here. A, B, C, D, E. But why didn't you include these? Because those are value nodes. They don't do anything. So tell me something. What does A, B, and C, D do? They maximize, right? So we're going to write right in front of them. Maximize, 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 and maximize. Then what does E and F do? You see E and F is trying to minimize it. Minimize, minimize, and G is of course maximize. Okay. Now, what do? Step number 1, we start. Draw some lines before we start. Great. So step 1, your static value. Let's start at 4 and 8. Now, your A is going to choose one of these static values. So can I say, oh, no, not 4 and 8. Your static value is 4, right? Now A is saying, I need something max. I'll take anything that's greater than or equal to 4. We can't decide anything yet. So let's go to step 2. Your static value now is 8. So let's write 8. Now you're saying, okay, I've confirmed my value to 8. Yes or no? We have said like, okay, see, my static value is bigger, so confirm. Now, since you have an 8 here, in the same step, you complete this triangle, you will throw it to the next level. Yes or no? So let's do that. Let's throw it to the next level. The next level is E, right? So let's throw it to E. E is a minimizing layer which wants something lesser than or equal to 8. Now let's do step 3. Static value is now, so let's write 9. Now we can't say anything about the triangle. No, we look. Now B wants something that's greater than or equal to 9. This is already set to 8. We want something that's lesser than or equal to 8, right? But he's giving something that's greater than or equal to 9. We don't want that. So what we're going to do is, in the same step, okay, we wrote B is greater than or equal to 9, and we want E is something lesser than or equal to 8. So here we will set E is equal to 8. Getting it? Because the range that will give, I will give you something greater than 9 is what B is saying. E is saying, Tambi, I want something that's lesser than 8. You see this clear difference? Nothing is overlapping. Overlapping means it will be like this. Okay, there is some range that we can agree on, but there is nothing they're agreeing on, no? Right? Okay. So what did we write? We said, okay, my static value is 9. When I chose 9, I know that my B is definitely going to be greater than or equal to 9. If my B is definitely going to be greater than or equal to 9, I can definitely say, I want something lesser than 8 pa. So I'll confirm. I don't want what you're giving. Okay, done. So now we'll just leave that, let that be, meaning we have skipped a value. So now we will say here, skip 3. Now let's go to the next one, C. So it for the static value is 2, this is 8, and this one is, B is not confirmed. Oh, okay. We will do something that's greater than or equal to 9. Even if there's 100 here, that 100 will get registered, but we don't want that. So we'll just let this be, okay? We have a 9 there, you have a 2 here, static value of, there we go. So now C wants something, C is a maximizing layer, C wants something that's greater than or equal to 2. Fine, this is set. Yeah, and remember to write all the values. Now let's go to the fifth static value, minus 2. We'll write minus 2. This is 8. This is that. C is, we want something greater than or equal to 2, but now we are sure that I don't want minus 2. I'm done with it, right? Now we move this to the next level. We give it to node F. We are saying to F, hey, take 2. So F definitely wants something lesser than or equal to 2 because it's a minimizing layer, right? Okay, so now let's go to step number 6. Oh, you know what? Let's not go to step number 6. You just first draw the graph like that. Now you know that you are comparing F with G, right? Oh, we have sent it to G, right? Oh, we sent 8 to G. 1 second. So we'll need to move this, right? So can I say now at step number 4, we are looking at E. E is filled, right? E is filled. So let's pass it on to G. G is a maximizing layer. So G must want something definitely that's greater than or equal to 8. So once we confirm this itself, we must confirm this greater than or equal to 8, greater than or equal to 8. Done. So you know what? We didn't need to move that. So here we want something greater than or equal to 8, greater than or equal to 8. Okay. Now when we got lesser than or equal to 2 here, right? This is an 8 here. Look at the difference here. This wants something lesser than 8. This will give something less than or equal to 2. It wants something more than 8. G wants something more than 8. But if you're going to give something less than or equal to 2, then why even bother about it? So it's just going to be 8. We are confirming it at 8. Right, so that's it. I think you can finish with step 5. So with this, you can say that you skipped 9 and minus 1. So bro, that's it enough for 10 marks? No. What do you need to write for 10 marks? You need to write branching factor is equal to 2. You need to write depth is equal to 3. You need to write number of nodes is equal to b power d, that is equal to 2 power 3, that is equal to 8. Then you need to write number of nodes computed is equal to, you skipped 3 nodes, meaning you computed 5 nodes. So your percentage computation saved is you saved 3 out of 8 nodes into 100%. So how much ever that is, that's almost 37 saved. What else do you need? What else do you need? What else? Final path. Yeah. We need to write your final path is equal to GEA 5. So you need to write that. You need to write this. You need to write this. P, D, number of nodes skipped. You need to write skipped nodes. Done.